When you think of modern Australia, you picture a harsh landscape filled with the most venomous snakes, deadly spiders, and apex predators on Earth. It holds a global reputation as a continent actively trying to eliminate its inhabitants. But from a strict paleontological standpoint, the Australia we observe today is just a pale, tamed shadow of a forgotten biological battleground. The venomous creatures and barren outback of the present are merely the surviving remnants of a much darker, far more extreme ecological laboratory. Millions of years ago, this massive landmass broke away from the ancient supercontinent and drifted into complete geographic isolation, severing all genetic exchange with the rest of the planet. What evolved here was a bizarre and brutal hierarchy. Without the presence of modern placental mammals to dominate the food chain, the ecosystem was conquered by giant marsupials, terrestrial crocodiles with serrated teeth, and massive, cold-blooded reptilian kings. It was an environment driven by severe, cyclical climatic starvation, forcing nature to weaponize every available biological trait just to endure. Today, we are exploring prehistoric Australia, the most dangerous place that ever existed. Before we uncover the fossil records and the biomechanics of these lost apex predators, please take a moment to hit the like button, subscribe to the channel, and leave a comment below letting us know exactly where in the world you are and what time it is as you are watching this. Let us step back into the Pleistocene epoch and examine the ultimate evolutionary test of survival. The story of prehistoric Australia does not begin with flesh and bone, but with the massive, grinding mechanisms of the Earth itself. To understand the extreme biological warfare that defined this continent, we must first look at the geological engine that isolated it. Around 180 million years ago, the landmass we now call Australia was firmly locked within the ancient supercontinent of Gondwana. It was connected to what is now South America, Africa, India, and Antarctica, sharing a vast, continuous ecosystem characterized by lush, temperate rainforests. But the Earth is a dynamic system driven by deep mantle convection, and this unified biological network was destined to be torn apart. Around 45 million years ago, a profound tectonic divorce occurred. The Australian plate finally severed its last terrestrial connection with Antarctica, breaking away and beginning a slow, relentless drift northward toward the equator. This was not merely a shift in geography, it was the creation of a closed ecological system. The landmass of Sahul, which encompassed modern Australia, Tasmania, and New Guinea, became a massive, floating biological quarantine zone. The physical separation from Antarctica triggered a cascading series of oceanographic and climatic consequences that would permanently alter the trajectory of life on Sahul. As the gap between the two continents widened, it opened the Tasman Gateway. Simultaneously, the Drake Passage opened between South America and Antarctica. These deep water channels allowed the formation of the Antarctic Circumpolar Current. This massive, uninterrupted ocean current acted as a thermal barrier, trapping cold water around the southern pole. Without the transfer of warm equatorial waters, Antarctica rapidly froze into an icehouse state. The global climate cooled, locking up vast amounts of fresh water in polar ice caps and causing global sea levels to drop significantly. For Sahul, the establishment of this freezing polar current meant a drastic reduction in atmospheric moisture. The continent was pushed northwards at a tectonic sprint of roughly 7 centimeters per year, moving directly into the mid-latitude high-pressure belt. This specific latitudinal zone is dominated by descending dry air masses, which actively suppress rainfall. The lush, temperate rainforests that once blanketed the continent began to retreat to the coastal fringes, replaced by expanding arid zones and dry sclerophyll forests. The most critical consequence of this tectonic migration was the complete severance of genetic exchange. In evolutionary biology, geographic separation acts as a massive pressure cooker through a process known as vicariance. Because there was no overland dispersal route available, whatever genetic material happened to be on the Sahul plate at the moment of separation became the absolute limit of the biological toolkit for the next several million years, while the rest of the terrestrial world remained somewhat connected, allowing the continuous migration, hybridization, and competition of various species. Sahul was cut off by deep oceanic trenches. As the Australian plate collided with the Pacific and Eurasian plates over millions of years, it pushed up a complex archipelago in what is now Indonesia, but it never formed a complete land bridge to the Asian mainland. This geographic reality established a definitive biological boundary known to modern science as the Wallace Line. Named after the 19th century naturalist Alfred Russel Wallace, this invisible barrier marks a deep water trench that prevented Asian fauna from crossing over into Sahul. Even during periods of intense global glaciation, when sea levels plummeted by over 100 meters and shallow continental shelves became exposed land bridges, the dark, plunging trenches of the Wallace Line remained utterly impassable to terrestrial animals. This absolute biological quarantine occurred at a critical juncture in mammalian evolution. On the massive, interconnected continents of the Northern Hemisphere, a new lineage of animals was rapidly rising to global dominance, the placental mammals. These creatures, which gestate their young internally through a highly advanced placental nutrient exchange system, proved incredibly efficient at outcompeting other mammalian forms. But the deep oceanic trenches of the Wallace Line acted as a perfect defensive wall. The placental predators and competitors that were aggressively conquering Asia, Europe, and the Americas simply could not reach the shores of Sahul. Because the placental invasion was abruptly halted at the ocean's edge, the existing inhabitants of the Australian plate were left entirely to their own evolutionary devices. The biological vacuum created by the absence of advanced placental mammals offered a vast array of empty ecological niches. The animals that inherited this isolated laboratory were the marsupials, which give birth to highly underdeveloped young that complete their growth in an external pouch, alongside ancient egg-laying monotremes, primitive terrestrial reptiles, and giant flightless birds. Furthermore, the isolation prevented geological renewal. Unlike active collision zones that push up massive, new mountain ranges like the Himalayas, much of the Australian interior remained flat and geologically quiet. Over millions of years, heavy weathering leached the soil of essential nutrients, particularly phosphorus and nitrogen. With no new volcanic activity in the deep interior to replenish the topsoil, the continent developed a severely low-calorie botanical baseline. Plants grew tough, toxic, and incredibly difficult to digest. This meant the herbivores of Sahul had to maximize their digestive efficiency to extract minimal energy from poor forage, which in turn forced the carnivores to become brutally efficient at killing to conserve calories. Without the evolutionary pressure of placental predators like true cats, dogs, or bears, the marsupials and reptiles of Sahul underwent massive adaptive radiation. They diversified rapidly, mutating to fill every available role in the ecosystem. The tectonic isolation of Sahul essentially locked its inhabitants into an internal biological arms race. It was an environment where ancient lineages, shielded from global competition, were subjected to the localized torture of a deteriorating climate and starving soils, setting the stage for a continent ruled by bizarre giants and heavily armed predators. In the biological history of the planet, ecological dominance is usually a matter of who gets there first and who possesses the most adaptable anatomical architecture. Across the vast landmasses of North America, Eurasia, and Africa, the undisputed champions of the terrestrial food chain were the placental mammals. These animals, armed with complex internal gestation systems, outcompeted nearly everything in their path. They radiated into saber-toothed cats, massive dire wolves, and swift, hooved herbivores. But because the deep oceanic trenches effectively quarantined the Australian tectonic plate, this invasion of placental mammals was entirely blocked. This geographical lockout created a rare phenomenon in natural history, an isolated, continent-wide biological vacuum. Nature absolutely abhors an empty ecological niche. Without lions, wolves, or bears to patrol the forests and plains, an immense opportunity opened up for the animals that had been trapped on the Australian plate since its separation from Antarctica. These inherited survivors were predominantly marsupials. For a long time, early paleontology misunderstood marsupials, classifying them as primitive or somehow evolutionarily inferior to placental mammals. This misconception stemmed from their bizarre reproductive strategy. Instead of nourishing a fetus through a complex placenta until it is fully formed, a marsupial gives birth to a highly altricial, practically embryonic neonate. This tiny pink organism, often no larger than a jelly bean, must blindly crawl up its mother's fur, enter an external pouch, and fuse to a teat to complete its development. While this seems fragile, in the context of prehistoric Australia, it was an absolute superpower. The continent was trapped in a cycle of severe, unpredictable climatic shifts. In a landscape defined by sudden droughts and widespread starvation, the placental reproductive method is a massive liability. A placental mother is locked into a high-energy pregnancy. If a severe drought hits, both the mother and the fully dependent fetus are likely to die from caloric exhaustion. A marsupial mother, however, possesses ultimate biological flexibility. If the environment collapses, she can simply abandon the joey in the pouch, drastically cutting her energy expenditure to ensure her own survival. Furthermore, many marsupials developed a physiological mechanism known as embryonic diapause. They can freeze the development of a fertilized embryo at the blastocyst stage, holding it in suspended animation for months until the heavy rains return and the environment can support lactation. This extreme energetic efficiency allowed marsupials to weather the brutal climate, but it came with a strict biomechanical limitation known as the forelimb constraint. Because that tiny, undeveloped neonate must pull itself from the birth canal up into the pouch, its front limbs must be heavily muscular and equipped with grasping digits from the very moment of birth. Because the forelimbs are biologically locked into this grasping architecture early in development, marsupials can never evolve hooves like a horse or flippers like a whale. Their evolutionary pathways were physically restricted. However, what is a limitation for an herbivore becomes a devastating weapon for a predator. The absolute necessity of strong, grasping forelimbs meant that when marsupials evolved to hunt, they were naturally pre-equipped with powerful arms and tearing claws. With these biological ground rules established, the marsupials underwent a massive wave of adaptive radiation. Through a process called convergent evolution, they began to morph into shapes that eerily mirrored the placental mammals across the oceans. Convergent evolution dictates that completely unrelated species will develop identical physical traits if they are subjected to the exact same environmental pressures. Because prehistoric Australia had open grasslands, dense forests, and burrowing prey, the marsupials evolved to exploit those exact same resources, wearing familiar disguises but running on a completely different genetic operating system. Slowly, the herbivores grew to massive proportions to process the low-nutrient vegetation, becoming giant walking energy reserves. To harvest this vast amount of meat, predatory marsupials abandoned a diet of insects and small reptiles and scaled up. They evolved robust jaw musculature and sharp, shearing premolars capable of slicing through thick hide and muscle. We see the rise of the Thylacoleo family, the marsupial wolves. Over millions of years, these creatures developed a skull and skeletal structure so perfectly adapted to running down prey that their remains are nearly indistinguishable from placental canines. A trained osteologist has to carefully examine the palatal fenestrae, the holes in the roof of the mouth, and the specific inward angle of the lower jaw to prove a thylacine skull is not from a dog. Alongside the pursuit predators, the Dasyuridae lineage produced heavily built, hyper-carnivorous scavengers and ambush hunters. These animals functioned as the marsupial equivalents of wolverines and badgers, packing immense bite forces into compact, muscular frames designed to crush bone and consume entire carcasses, leaving no waste in a nutrient-poor environment. Without a single placental predator to challenge them, the marsupials engineered a parallel universe of predation. They transformed from small, nocturnal insectivores into highly specialized killers, perfectly optimized to dominate a continent where every single calorie had to be violently extracted from the landscape. The evolution of prehistoric Australia's megafauna was not dictated by competition alone. It was forced by the relentless, crushing pressure of a deteriorating climate. As the Australian plate drifted northward into the arid, high-pressure belt, the continent began a slow, irreversible slide into desiccation. This was not a linear progression, but a volatile, oscillating process. The deep-time paleoclimatological record, retrieved from lake sediments and cave deposits, reveals that Sahul was defined by the ancient precursors of the El Niño Southern Oscillation. These climate cycles created a landscape of extreme contrast, where long periods of lethal drought were punctuated by rare, devastating flash floods. This environmental instability became the primary filter for natural selection. In an ecosystem where food and water sources could disappear for years, the biological winners were not the fastest or the most aggressive, but the most energy efficient. This necessity birthed a unique evolutionary trajectory known as the starvation survival strategy. Every creature on the continent, from the smallest lizard to the largest herbivore, became an expert in caloric management. The flora of Sahul adapted by producing high levels of secondary metabolites, essentially natural toxins and defensive chemicals, to prevent herbivores from overgrazing their limited leaf mass. In response, the herbivores had to evolve highly specialized digestive systems to detoxify this forage. This meant they had to spend more time processing food, leading to a slower metabolic rate. This slow metabolism trend created a ripple effect through the entire food chain. If the herbivores were moving and metabolizing at a slower pace to conserve energy, the predators did not need to be high-speed endurance runners like the wolves or cats of the Northern Hemisphere. Instead, the predatory landscape of Sahul prioritized explosive, high-impact force over sustained aerobic pursuit. This energy-optimized predation forced the carnivores to rely on ambush tactics and massive singular bite forces rather than exhausting chases. The evolution of a predatory marsupial was essentially an exercise in minimizing the calories burned per kill. The paleoclimatological data also highlights the role of the continent's topography in this optimization process. Because Sahul was geologically stable and largely flat, there were very few thermal refuges. In mountainous continents, animals can migrate to higher elevations to follow shifting climate zones as temperatures rise or fall. In Australia, that option was non-existent. When the droughts hit, the animals were forced to congregate around shrinking, scattered waterholes. These waterholes became the ultimate focal points of prehistoric biological activity. They were the sites of both critical survival and the most intense predation events. This geographic reality forced the megafauna to develop high levels of biological mobility. The largest creatures, like the Diprotodon, evolved to be biological tanks capable of massive, long-distance treks across the arid interior. They became living reservoirs, utilizing thick, metabolically inactive adipose tissue to survive the long, dry marches between water sources. This physiology is distinct from the placental giants of other continents, which often evolved toward high-energy, fast-growing body plans. The Sahul megafauna were the masters of the long game, built for persistence rather than peak performance. The scientific consensus regarding this climatic pressure is that it essentially locked the continent into a specific evolutionary direction. Because the continent could not support a high density of biomass, the population numbers of these giant species were likely always relatively low. This made them incredibly vulnerable to any external stressor. If you have an ecosystem where the energy baseline is extremely thin, and every organism is already optimized to the edge of its physiological limit to conserve energy, there is zero margin for error. Furthermore, the lack of seasonal nutrient spikes, the equivalent of a northern spring where grasses explode with protein, meant that these animals had to maintain their efficiency year-round. This led to a reliance on low-quality forage, which meant their bodies had to be massive just to house the fermentation vats required to break down high-fiber, toxin-rich plant matter. The giant size of creatures like the Procoptodon or the Diprotodon was not just a side effect of evolution. It was a mandatory structural requirement for a digestive system that had to extract every available calorie from a nutrient-depleted landscape. As the paleoclimatological record continues to be refined through studies of stalagmites and fossilized pollen, it becomes clear that the prehistoric Australian ecosystem was a machine built for durability. The entire food web was tethered to the water cycle. When the climate shifted, the animals did not have the luxury of evolving new behaviors quickly. They were slaves to their own physiological specializations. The evolution of Sahul's megafauna was a desperate, slow-motion optimization project, where nature was constantly trimming the metabolic fat to ensure that, even in the worst droughts, the spark of life would not be extinguished. This was a place where energy was the most precious currency, and the most dangerous predator was not always the one with the biggest teeth. It was the one that knew how to wait the longest. In the shadowed woodlands and dry savannas of Pleistocene Sahul, the apex predator role was not solely monopolized by mammals. The harsh, low-energy environment created the perfect conditions for a cold-blooded giant to ascend to the top of the terrestrial food chain. This was Varanus priscus, historically recognized by the scientific name Megalania, the absolute largest terrestrial lizard to ever exist. Reaching lengths of up to 7 meters and weighing hundreds of kilograms, it was a hyper-carnivorous monitor lizard that actively hunted the massive marsupial herbivores of the era. However, the true terror of Varanus priscus did not stem merely from its sheer size, but from the highly specialized biomechanical engineering of its skull and a biochemical weapon system that has only recently been fully understood by modern science. Mammalian predators, such as the big cats of the Northern Hemisphere, typically kill by utilizing a massively reinforced skull driven by enormous jaw muscles. They rely on high bite forces to crush the windpipe or snap the cervical spine of their prey. The biomechanical structure of the Varanus priscus skull operated on a completely different, yet equally devastating architectural principle. Paleontological analysis of the cranial remains reveals a skull that was relatively lightweight, characterized by significant fenestration. These large natural openings in the bone reduced overall weight while maintaining critical structural integrity. Furthermore, the skull was highly kinetic. Unlike the rigidly fused cranium of a mammalian carnivore, the skull of Varanus priscus possessed multiple flexible joints. The most critical of these adaptations was the intramandibular hinge, a specialized flexible joint located in the lower jaw. This hinge allowed the jaw to bow outward and absorb the immense multidirectional stress generated by struggling prey. Varanus priscus did not possess the bone-crushing bite force of a mammalian apex predator, nor did it need to. The skull was explicitly designed for a kinetic slicing attack, rather than a sustained, suffocating grip. The primary weapons were housed within the jaw margins, dozens of backward, curving, blade-like teeth featuring deeply serrated edges, a dental configuration known to science as xiphodont. When Varanus priscus struck a giant herbivore, the biomechanical goal was to inflict maximum trauma in minimum time. The lizard would drive its serrated teeth deep into the muscle tissue and then aggressively pull backward, utilizing its massive, heavily muscled neck to literally rip massive sections of flesh from the target. This bite and slice mechanism inflicted catastrophic physical trauma, severing major arteries, slicing through deep muscle tissue and tearing tendons in a fraction of a second. For decades, paleontologists believed that this massive mechanical trauma, combined with subsequent, slow-acting bacterial infections from the bite, were the primary mechanisms of death for its prey. However, modern scientific breakthroughs in the field of evolutionary toxinology have fundamentally rewritten our understanding of this prehistoric giant. The critical pivot in this paradigm comes from the intensive study of a specific reptilian clade known as Toxicophora. This evolutionary classification unites snakes, iguanians, and monitor lizards under a single phylogenetic umbrella, establishing that they all share a common, ancient, venomous ancestor. Advanced magnetic resonance imaging and transcriptomic analysis of the Komodo dragon, which serves as the closest living ecological and genetic analogue to Varanus priscus, revolutionized this field. Scientists discovered the presence of highly evolved complex venom glands located entirely within the lower jaw. Unlike highly derived venomous snakes, which use specialized hollow fangs to inject neurotoxins under high pressure, monitor lizards utilize an anatomically simpler, lower-pressure delivery system. The venom is secreted from the mandibular glands and flows out through ducts between the teeth, mixing with the saliva. It actively enters the prey through the massive lacerations created by the serrated teeth during the violent pulling action of the bite. Because Varanus priscus belongs to the exact same varanid lineage, the overwhelming scientific consensus heavily supports the hypothesis that this giant Pleistocene predator also possessed these mandibular venom glands, scaled up to monstrous proportions. This paradigm shift transitions the animal from a purely mechanical killer to the largest venomous vertebrate in the history of the Earth. The chemical composition of this venom provides insight into the predatory efficiency of the lizard. The venom of these giant monitors is not the rapidly acting neurotoxic variety found in elapid snakes, which immediately paralyzes the respiratory system. Instead, the biochemical cocktail is profoundly hemotoxic. It contains complex proteins and enzymes that actively target the cardiovascular system of the prey. When injected into the bloodstream, these proteins induce a rapid, artificial drop in blood pressure by causing the smooth muscle lining the blood vessels to relax. This induces immediate systemic shock. Simultaneously, other enzymes act as powerful anticoagulants, preventing the blood from clotting at the site of the wound. When Varanus priscus ambushed its prey, the initial strike caused immense physical tissue damage, creating deep, ragged wounds. The hemotoxic venom immediately entered the bloodstream through these massive lacerations. As the prey broke free and attempted to flee, the venom artificially sustained the bleeding and induced profound, paralyzing hypertension. The giant marsupial would quickly succumb to hypovolemic shock, collapsing from massive, uncontrollable blood loss. For Varanus priscus, this combined mechanical and chemical assault was the ultimate metabolic cheat code. As an ectotherm, a cold-blooded organism relying entirely on external environmental heat to regulate its body temperature, it simply could not afford the massive caloric expenditure of a prolonged, high-speed pursuit or a sustained wrestling match with a massive, desperate herbivore. The venom delivery system allowed the giant lizard to execute a single, catastrophic strike, retreat to a safe distance to avoid retaliatory injury, and simply track the bleeding prey via chemosensory tongue flicking until the animal collapsed. This biomechanical and biochemical synergy made Varanus priscus a uniquely adapted nightmare, perfectly exploiting the energy constraints of the Sahul environment by guaranteeing a lethal outcome with absolute minimal caloric risk to the predator. When we picture a crocodile, the image is universal. We see a heavily armored, low-slung reptile lurking silently just beneath the surface of a murky river. For tens of millions of years, the crocodilian body plan has been the ultimate blueprint for aquatic ambush predation. They are perfectly engineered to explode from the water, clamp down with conical teeth designed for holding, and drag their victims into the depths to drown. But what happens to the ultimate aquatic assassin when the water completely disappears? In prehistoric Australia, the answer was a terrifying evolutionary reversal. As the continent drifted northward, an intense aridification wiped out the vast inland lake systems and permanent rivers. A unique lineage of crocodiles was forced to make a radical choice. They could either perish in the drying mud, or they could abandon their aquatic heritage, climb out onto the baking plains, and hunt on dry land. This evolutionary desperation gave rise to Quinkana, a fully terrestrial crocodile that actively chased down its prey. To transform a water-dwelling ambush predator into a land-based hunter, nature had to execute a complete biomechanical overhaul of the crocodilian skeleton. The first and most critical adaptation was the complete redesign of its locomotion system. Modern crocodiles possess a sprawling posture where their legs project outward from the sides of their bodies. This is highly efficient for swimming and resting on riverbanks, but it is incredibly inefficient and exhausting for traveling long distances or running down prey on land. Quinkana solved this by evolving a semi-erect stance. Its limbs grew significantly longer and were positioned much further underneath its body, supporting its weight directly against gravity. This structural shift fundamentally changed how the animal moved. Instead of dragging its belly across the earth in short, energy-draining bursts, Quinkana could lift its body clear off the ground and engage in a sustained, stride-based walk. Biomechanical models suggest that these elongated, powerful legs allowed it to pursue the giant, slow-moving marsupial herbivores across the dry savannas with a terrifying, rhythmic efficiency, completely detaching it from the need for deep water cover. However, upgrading the suspension system was only half the battle. The most significant evolutionary shift occurred in the skull and the teeth, driven by the absolute necessity of changing how the animal actually killed. An aquatic crocodile relies entirely on the presence of deep water to finish the job. Its teeth are conical, like thick metal spikes, designed exclusively to puncture and hold struggling prey so it can be dragged under and drowned. But on the dry plains of Sahul, you cannot drown a giant kangaroo or a massive wombat. You have to kill it through pure mechanical trauma. Therefore, Quinkana completely discarded the traditional crocodilian dental blueprint. In place of rounded spikes, it evolved xiphodont dentition. These were laterally compressed, blade-like teeth featuring deeply serrated edges, strikingly similar to the teeth of the giant carnivorous dinosaurs that had dominated the Earth millions of years prior. Coupled with these serrated blades, the very shape of the skull transformed. Rather than the broad, flat snout of a modern river crocodile, which is designed to sweep rapidly through water with minimal resistance, Quinkana developed a deep, narrow, and heavily reinforced snout. This deep skull architecture was vital for absorbing the massive vertical stress and impact forces generated when biting into a large terrestrial animal. When Quinkana attacked, it did not grab and hold. It slammed its heavy jaws closed, driving the serrated teeth deep into the muscle, and then used the sheer power of its neck and body weight to rip backward. Just like the giant monitor lizards it shared the landscape with, Quinkana killed by inflicting catastrophic blood loss. It would slice through major arteries and tendons, crippling the target and letting it bleed to death on the open plains. The existence of Quinkana represents a fascinating convergence of evolutionary pressures. In any other ecosystem, this terrestrial hunting niche would have been immediately filled by large mammalian predators like wolves or big cats. But because Sahul was entirely isolated behind deep oceanic trenches, no advanced placental carnivores were present to claim the role. Quinkana stepped out of the drying rivers to exploit this massive ecological void. It became a reptilian substitute for a cursorial mammalian predator. Yet, despite adopting the hunting style of a wolf, Quinkana retained the ultimate survival advantage of its reptilian heritage: cold-blooded energy efficiency. A mammalian predator of equivalent size would require a massive and constant intake of calories to maintain its internal body temperature, a severe liability during the prolonged, brutal droughts that defined the Australian climate. Quinkana, on the other hand, operated on a fraction of that energy budget. It could utilize the blazing heat of the sun to power its muscles for the hunt, and then simply power down during periods of severe starvation. It did not need to eat every week. It could survive for months on a single, massive kill. This synthesis of a highly mobile, land-running skeletal architecture, a dinosaur-like slicing bite, and a fiercely economical, cold-blooded metabolism made Quinkana one of the most uniquely adapted predators of the Pleistocene epoch. It was a stark reminder of the sheer adaptability of life. When the continent dried up and the rivers turned to dust, this crocodile did not simply fade into extinction. It stood up on 4 long legs, sharpened its teeth into blades, and claimed the dry land as its new hunting ground, proving that in prehistoric Australia, even the reptiles were willing to rewrite their entire biological history just to survive the harsh reality of the landscape. In the shrinking, desperately crowded ecosystems surrounding the few remaining permanent water sources of Pleistocene Sahul, death did not always come with tearing claws or venomous fangs. Sometimes it emerged silently from the mud and reeds as a massive, muscular cylinder. This was Wonambi narracortensis, a giant constrictor snake that reached lengths of over 5 meters and weighed up to 100 kilograms. However, classifying Wonambi simply as a giant python is a major taxonomic error. Modern genetic and morphological analysis places this creature within the Madtsoiidae family, an ancient lineage of primitive snakes that shared the Earth with the dinosaurs. While this family went extinct across the rest of the globe millions of years prior, the absolute geographic isolation of the Australian plate provided a sanctuary, allowing these prehistoric serpents to survive and scale up into apex predators. Unlike the highly mobile, warm-blooded mammalian hunters, Wonambi was a master of static predation. It lacked the advanced thermal sensory pits found in modern pythons and possessed a relatively rigid, primitive jaw structure that could not unhinge to the extreme degrees seen in contemporary snakes. This meant it could not swallow the absolute largest of the megafauna, but instead targeted juvenile diprotodons, large wallabies, and giant flightless birds that came to the water's edge to drink. The hunting strategy relied entirely on flawless camouflage and an explosive close-range strike. The snake would anchor its heavy tail around a submerged log or rock, lunging with terrifying speed to bury its backward-curving teeth into the face or neck of the prey. But the bite was merely a grappling hook. The true weapon was the animal's immense muscular anatomy. For decades, biological science operated under the assumption that constrictor snakes killed by mechanical asphyxiation, essentially suffocating the prey by preventing the lungs from expanding. Modern cardiovascular monitoring of simulated predation events has completely overturned this hypothesis. When Wonambi threw its heavy coils around a struggling marsupial, it was not merely cutting off the air supply, it was engineering a catastrophic, localized cardiovascular collapse. Every time the prey exhaled, the snake tightened its grip, incrementally increasing the internal intrathoracic pressure. Within seconds, this immense mechanical force exceeded the pumping capacity of the victim's heart. The blood vessels were physically squeezed shut, stopping the flow of oxygenated blood to the brain. This mechanism, known as complete circulatory arrest, induces rapid unconsciousness and death in a fraction of the time it would take an animal to suffocate. The sheer tensile strength required to physically stop the heart of a robust, heavily muscled Pleistocene herbivore points to an animal composed of incredibly dense, fast-twitch muscle fibers. The existence of a giant, ancient snake dominating the waterholes brings us to one of the most critical scientific questions regarding prehistoric Australia. Why were cold-blooded reptiles competing so effectively against warm-blooded mammals for the highest trophic levels? To understand this, we must examine the biological economics of thermoregulation. Mammals and birds are endotherms. They maintain a high, constant internal body temperature regardless of the outside environment. This physiological engine allows them to sustain high-speed pursuits, hunt at night, and survive in freezing climates. However, this engine requires massive amounts of fuel. Up to 80 or 90% of the calories a mammalian predator consumes are burned strictly to generate body heat. In a lush, resource-rich environment like Pleistocene North America, this high caloric tax is manageable. But on the starving, drought-stricken plains of Sahul, a high basal metabolic rate was an incredible evolutionary liability. An apex mammalian predator, like the marsupial lion, had to kill frequently just to keep its internal furnace running. If the rains failed and the prey populations crashed, the warm-blooded hunters starved to death at an accelerated rate. Ectotherms like Wonambi, Megalania, and Quinkana bypassed this vulnerability entirely. Because they relied on the ambient temperature of the sun and the earth to heat their blood, their basal metabolic rate was a tiny fraction of a similarly sized mammal's. This ectothermic physiology granted Wonambi the ultimate superpower in a volatile climate: the ability to wait. Modern physiological studies on large constrictors reveal that between meals, they essentially shut down their internal biological processes. They can reduce their heart rate, allow their digestive tract to atrophy, and drastically lower their oxygen consumption. When Wonambi secured a large kill, the sudden influx of protein would trigger an extreme metabolic spike, rapidly rebuilding its digestive organs to process the massive meal. Once digestion was complete, the snake could power down again, surviving for over a year without eating another bite. In an ecosystem defined by extreme boom and bust cycles, the ability to turn off your metabolism is a far greater survival trait than the ability to run fast. This energy-efficient sit-and-wait strategy made the giant reptiles of Australia the undisputed masters of the long droughts. But this supreme biological specialization came with a fatal flaw. Ectotherms are entirely tethered to the environmental temperature. If the climate shifts too rapidly, or if the protective cover of the landscape is burned away, their slow metabolism prevents them from quickly migrating or adapting to new biomes. Furthermore, Wonambi's reliance on ambush tactics made it heavily dependent on the dense vegetation surrounding permanent waterholes. As the continent continued its slow, brutal trajectory toward complete aridification, the ancient lakes and rivers began to vanish, taking the giant serpents' hunting grounds with them. The very metabolic strategy that allowed them to conquer the harsh Australian interior ultimately bound their fate directly to the disappearing water. When 19th century paleontologists first unearthed the fossilized skull of the apex mammalian predator of Pleistocene Australia, they made a logical, yet entirely incorrect assumption. Based on the sheer size of the cranium and the terrifying blade-like teeth, they named it Thylacoleo Carnifex, which translates to the absolute executioner marsupial lion. The name evokes the image of a feline, a sleek, fast-running pursuit predator. However, a deeper examination of its phylogenetic tree reveals a far more bizarre evolutionary reality. Thylacoleo was not a cat, nor was it even closely related to the marsupial wolves or the carnivorous dasyurids that populated the continent. Its closest living relatives are the modern koala and the wombat. Thylacoleo was a member of the Diprotodontia order, a lineage composed almost entirely of docile herbivores. It represents one of the most extreme evolutionary pivots in the history of biology, a plant-eating lineage that brutally forced its way into the hyper-carnivorous apex predator niche. When a herbivorous architecture is aggressively modified by natural selection to process meat, the resulting biological hardware is entirely unprecedented. Evolution rarely builds from scratch, it modifies the existing framework. Because the ancestors of Thylacoleo had practically lost their canine teeth to make room for chewing fibrous plants, The marsupial lion had no fangs. A mammalian predator without canines seems entirely unequipped for the job, as true placental carnivores rely almost entirely on elongated canines to act as precise daggers to puncture the windpipe or sever the spinal cord of their prey. To solve this biomechanical deficit, Thylacoleo weaponized its front teeth. The central incisors, the teeth typically used by rodents to gnaw or by kangaroos to crop grass, were massively enlarged. They protruded forward like serrated, heavy-duty spikes. These modified buck teeth became the primary puncturing weapons used to initiate the kill. But the true horror of the Thylacoleo skull lay further back in the jaw. Mammalian carnivores typically possess carnassial teeth, which are specialized molars adapted for tearing flesh. Thylacoleo discarded this standard blueprint. Instead, its third premolars were stretched and elongated into massive, continuous, steel-like blades. These teeth were the largest shearing structures possessed by any known carnivorous mammal. When the jaw closed, these upper and lower premolars bypassed each other with zero clearance, operating exactly like a pair of heavy industrial meat shears. They did not crush, they cleanly sliced through thick hide, heavy muscle tissue, and solid bone with terrifying efficiency. To power these biological bolt cutters, the skull of Thylacoleo underwent extreme structural reinforcement. The zygomatic arches, the cheekbones that anchor the jaw muscles, were incredibly wide and flared outward. This architectural expansion provided massive surface area for the attachment of the temporalis muscles, the primary engines of jaw closure. Furthermore, the snout was incredibly short, practically pug-nosed. In biomechanical engineering, shortening the distance between the pivot point, which is the jaw joint, and the applied force, which are the teeth, creates a massive mechanical advantage. It turns the skull into a high-leverage crushing machine. When paleontologists applied modern finite element analysis, essentially creating three-dimensional digital models to simulate the mechanical stress and force output of the skull, the results shattered existing biological records. When adjusted for body mass, Thylacoleo Carnifex possessed the absolute strongest bite force quotient of any known mammalian predator, living or extinct. A 100-kilogram marsupial lion bit down with more absolute mechanical destructive force than a 250-kilogram African lion. This extreme bite force was not designed for holding on to a struggling animal and waiting for it to suffocate. It was a single-strike execution mechanism. The jaw was engineered to instantly snap the thick cervical spine of a giant herbivore or completely crush its trachea in a fraction of a second. However, delivering this catastrophic bite required Thylacoleo to first catch and restrain animals that were often significantly larger than itself. Without the cursorial anatomy required for high-speed pursuits across the open savanna, the marsupial lion was strictly an ambush predator. It had to drop from the heavy branches of the dry sclerophyll forests, or explode from the dense underbrush at extremely close range. To secure its target, it utilized another anatomical quirk inherited from its tree-climbing ancestors: a highly specialized forelimb equipped with a pseudo-opposable thumb. Among terrestrial mammalian predators, an opposable digit is virtually unheard of. Paws are generally designed for running or digging, not for complex grasping. But Thylacoleo retained the grasping architecture of a koala, and evolution heavily militarized it. The opposable thumb was equipped with a massive, scythe-like, partially retractable claw. When the marsupial lion ambushed its prey, it did not merely swipe or strike, it grabbed. It would sink these massive thumb claws deep into the muscle and hide of a giant Diprotodon, locking its heavily muscled arms around the target like organic vice grips. Once anchored, the prey simply could not tear itself free. The postcranial skeleton further supports this grappling methodology. Thylacoleo was built incredibly low to the ground, with incredibly dense, heavy bones and a stiff, robust tail. Paleontological biomechanics suggests that this tail acted as a biological kickstand. Just like a modern kangaroo, Thylacoleo could rear back on its powerful hind legs and brace itself with its stiff tail, forming a highly stable tripod stance. This specialized posture completely freed both of its heavily armed forelimbs from the duty of supporting its body weight. It could grapple, slash, and pull the massive prey directly toward its mouth, anchoring itself firmly to the earth while it delivered the executioner's bite. Thylacoleo Carnifex was the ultimate expression of the prehistoric Australian predator paradigm. In a severely resource-depleted ecosystem, where energy was the most critical currency, high-speed chases were a massive metabolic liability. The marsupial lion solved the caloric equation by condensing the entire hunting sequence into a few seconds of overwhelming, hyper-violent mechanical force. It eliminated the exhausting struggle of the hunt by engineering a body designed purely for the instantaneous destruction of the central nervous system. It was a bizarre, heavily armored biological assassin, proving that when the environment demands absolute lethality, evolution can take the genetic blueprint of a docile tree climber and forge it into the most biomechanically devastating mammalian killer the planet has ever seen. To understand the sheer scale of the ecological pressures at play in prehistoric Australia, we must examine the ultimate survivor of the Pleistocene plains. This was Diprotodon, the absolute largest marsupial to ever walk the earth. Weighing up to 3 tons and possessing the heavy, armored build of a modern rhinoceros, Diprotodon was a walking biological tank. It was a creature of massive caloric requirements, needing vast quantities of vegetation and fresh water daily to sustain its immense bulk. This presents a profound biological paradox. How does a multi-ton, water-dependent herbivore survive on a continent that is actively undergoing a slow, relentless process of severe aridification? For decades, the movement and survival strategies of Diprotodon remained a paleontological mystery until modern science learned how to read the chemical memories locked inside its skull. While fossilized bones can reveal the biomechanics of an animal and how it died, the teeth provide a high-resolution biological flight data recorder of exactly how it lived. Diprotodon possessed incredibly specialized dentition, primarily characterized by a pair of massive, elongated front incisors. Much like the tusks of an elephant or the front teeth of a modern rodent, these giant incisors grew continuously throughout the animal's entire life. As the tooth extruded from the jaw, it laid down microscopic layers of dentin and enamel, day by day, year by year. This continuous growth process created a perfect chronological archive of the animal's interaction with the environment. To decode this archive, paleontologists turned to advanced geochemical technology, specifically the analysis of environmental isotopes. The Earth's crust is composed of various types of bedrock, and each geological region possesses a distinct chemical signature based on the specific ratios of heavy and light strontium isotopes. As rocks weather and break down, these specific strontium ratios leach into the surrounding soil and are dissolved into the local groundwater. When a plant grows in that specific region, it absorbs the water and incorporates that exact local strontium signature into its cellular structure. Finally, when a giant herbivore like Diprotodon consumes those plants and drinks from those local water sources, the strontium signature is permanently locked into the layer of tooth enamel forming at that exact moment. By taking cross-sections of fossilized Diprotodon incisors and utilizing precise laser ablation techniques to vaporize microscopic samples along the growth axis of the tooth, scientists can extract a continuous timeline of the animal's geographical location. If a Diprotodon spent its entire life in one single territory, the strontium isotope ratio within its tooth would remain as a flat, unchanging line. But when the mass spectrometers analyzed the teeth of Diprotodon, they did not find a flat line. They found a massive, highly predictable, and perfectly repeating sinusoidal wave. This oscillating chemical signature was a monumental discovery. It proved unequivocally that Diprotodon was not a stationary browser. It was a highly mobile, nomadic giant that undertook massive, seasonal, round-trip migrations across the harsh Australian interior. The isotope data suggests these herds were traveling up to 200 miles every single year. This was not random wandering. It was a desperate, highly calculated march, driven entirely by the shifting availability of surface water and the temporary flush of green vegetation triggered by the ancient monsoon cycles. In the field of ecology, this aligns perfectly with an extreme survival strategy forced by a volatile environment. Diprotodon was a classic example of an animal heavily invested in what biologists call K-selection. They grew slowly, lived long lives, and invested massive amounts of biological energy into raising a single offspring in their pouch at a time. A species with this slow reproductive rate absolutely cannot afford high adult mortality. Therefore, when the localized droughts set in and the vegetation turned toxic and fibrous, they could not afford to stay and starve. They had to mobilize. We must picture a prehistoric equivalent to the modern wildebeest migration across the African Serengeti, but populated entirely by giant, lumbering marsupials. Moving in massive, synchronized herds, Diprotodon became the ultimate ecological engineers of Sahul. The sheer mechanical force of thousands of 3-ton animals marching across the continent would have physically shaped the landscape, carving deep, permanent migration highways into the earth, trampling competing vegetation and aggressively pruning the canopy. However, the very isotope data that reveals their incredible mobility also foreshadows their ultimate doom. The strategy of chasing seasonal waterholes across a drying continent is only viable as long as those waterholes eventually replenish. As the global climate shifted further into an ice age, locking up oceanic moisture and intensifying the aridity of the Australian landmass, the ancient monsoon cycles began to fail. The seasonal inland lakes that the Diprotodon herds relied upon for their annual migrations began to evaporate permanently. This desperate reliance on shrinking water sources created some of the most tragic and spectacular mass mortality assemblages in the paleontological record. At sites like Lake Callabonna in South Australia, scientists have uncovered the remains of hundreds of Diprotodon individuals stacked on top of one another. As the vast inland lake dried up, turning into a treacherous expanse of deep, sticky clay, the starving, dehydrated herds were drawn to the last remaining puddles of water in the center. The heavy animals broke through the dry crust and became hopelessly bogged down in the deep mud. The fossil record captures entire family units trapped in the earth, dying of starvation and exposure, their continuous teeth recording the exact isotopic signature of their final, desperate days. The strontium data proves that these giants mastered the art of outrunning the drought for millions of years, until the continent simply ran out of water, turning their ancient migration routes into unavoidable death traps. When we observe the modern Australian landscape, the biomechanical signature of the macropod family is the high-speed hop. It is a highly specialized, elastic recoil system that practically defines the kangaroo. But as we dig deep into the Pleistocene fossil record, we encounter a massive skeletal anomaly that completely shatters this biological rule. Meet Procoptodon Goliah, the short-faced giant. Standing over 2 meters tall and weighing up to 240 kilograms, this was the absolute largest kangaroo to ever exist. But its sheer massive scale forced a catastrophic mechanical problem upon the species. It was physically too heavy to hop. To survive the brutal, resource-depleted environment of Sahul, Procoptodon had to completely re-engineer the macropod body plan, evolving an entirely different method of terrestrial locomotion. Independent bipedal striding. It walked on 2 legs, placing one foot in front of the other, exactly like a human being or a theropod dinosaur. To understand this evolutionary pivot, we must first analyze the physics of the hop. Modern kangaroos operate on a system of kinetic energy storage. Their massive Achilles tendons act as biological springs. When the animal lands, the tendon stretches, storing gravitational potential energy. As they push off for the next jump, that stored energy is violently released, propelling the animal forward with incredible metabolic efficiency. At high speeds, hopping is one of the most energy-efficient forms of land travel on the planet. However, this biomechanical system comes with a strict, unbreakable upper weight limit. As an animal's mass increases, the cross-sectional area of its tendons and bones must increase to handle the load. But the stress placed on those tissues during the landing phase of a hop increases at a much faster rate than the maximum tensile strength of the biological material. Biomechanical models utilizing finite element analysis demonstrate that if a 240-kilogram animal attempted to execute a standard high-speed hop, the immense kinetic force generated upon landing would instantly exceed the structural limits of the biological tissue. The Achilles tendon would literally snap under the immense pressure, and the impact would shatter the tarsal bones in the ankle. The hop was mathematically impossible. Furthermore, hopping is only efficient at high velocities. Modern kangaroos are actually incredibly inefficient at slow speeds. To move slowly while grazing, they must rely on pentapedal locomotion, planting their heavy tail into the ground and using it as a fifth limb to support their entire body weight while they swing their hind legs forward. This is a massive metabolic drain. For a giant, 240-kilogram browser that spent its entire day slowly moving from tree branch to feed, this pentapedal crawl would be an absolute energetic catastrophe. The shift to bipedal striding completely eliminated this low-speed metabolic tax. Forced past the mechanical limits of elastic recoil, Procoptodon Goliah abandoned hopping and evolved a walking stride. This required a complete anatomical redesign of the lower half of its skeleton, particularly the pelvis and the ankle joints. In a hopping kangaroo, the legs move together in parallel, meaning the pelvis does not need to stabilize the body against side-to-side rotational forces. But when an animal walks independently, placing one foot in front of the other, it must balance its entire body weight on a single leg for exactly half of the stride cycle. To achieve this, the pelvis of Procoptodon became incredibly broad and heavily flared outward. This massive bony architecture provided maximum surface area for the attachment of highly enlarged gluteal muscles. These muscles acted exactly as they do in the human body, firing continuously to stabilize the hips and prevent the giant kangaroo from collapsing to the side with every single step it took. The structure of the ankle and the foot was fundamentally altered to support this new weight distribution. A hopping kangaroo has a highly specialized, elongated foot designed for maximum leverage. Procoptodon, however, possessed an incredibly short, rigid foot that terminated in a single, massive hoof-like toe, while the other digits were severely reduced or entirely lost. The ankle joint, specifically the articulation between the talus and calcaneus bones, was modified into a heavy, interlocking hinge. It restricted side-to-side movement entirely, transforming the lower leg into a solid, weight-bearing column designed to support massive vertical compression forces. The animal did not possess the flexible, elongated tendons required for bouncing. It was built on a chassis of thick bones and heavy ligaments designed for continuous, grinding forward momentum. This walking architecture was perfectly synchronized with the animal's ecological role. Procoptodon was not a grass eater grazing on the open plains. It was a high-reach browser that inhabited the dry, semi-arid woodlands. It possessed a short, incredibly deep skull, built to house massive chewing muscles, forward-facing eyes for advanced binocular vision, and incredibly long, highly articulated arms, ending in specialized, hook-like claws. It operated ecologically much like a giant, bipedal ground sloth. It would walk steadily through the dry scrub, rear up to its full, imposing height, and use its long arms to pull heavily branched, toxic foliage directly into its powerful, crushing jaws. The bipedal striding of Procoptodon Goliah represents one of the most fascinating examples of biomechanical problem-solving in the prehistoric world. When natural selection pushed the macropod body to an extreme, unsustainable mass, the animal could not simply scale up its existing locomotion system. It was forced to invent a completely new one. By widening the pelvis, locking the ankle joints, and learning to walk foot over foot, the giant short-faced kangaroo bypassed the structural limits of its own biology. It proved that in the unforgiving evolutionary laboratory of prehistoric Australia, when the traditional rules of anatomy fail, life will engineer a radically different pathway just to keep moving forward. The fundamental rule of biology on the Sahul landmass was absolute energy scarcity. When the soils are stripped of nutrients and the climate violently oscillates between drought and flood, the continent operates on a severe caloric deficit. In this starving arena, physical confrontation is a massive liability. Grappling, chasing, and overpowering a target burns precious energy reserves and risks physical injury. An injured predator in a harsh environment is a dead predator. To solve this thermodynamic problem, natural selection pushed the ecosystem toward the ultimate biological cheat code: chemical warfare. This extreme environmental pressure triggered a continent-wide phenomenon of convergent evolution, where entirely unrelated branches of the evolutionary tree independently developed highly sophisticated venom systems. We have already seen how the giant monitor lizard deployed hemotoxic saliva to induce shock, but the true mastery of this chemical weaponry was achieved by the front-fanged snakes, the Elapidae family. Today, Australia is uniquely famous for housing the most venomous land snakes on the planet. This is not a random geographical accident. It is the direct, calculated result of ancient ecological starvation. On continents with dense, reliable prey populations, predators can afford to be inefficient. If a wolf misses a rabbit, it will likely find another one the next day. But in the unpredictable, arid interior of prehistoric Australia, a predator might only encounter a viable meal once every few weeks. Therefore, when a strike occurs, the prey absolutely cannot be allowed to escape. To guarantee the kill, the venom of the Australian elapids evolved into a hyper-concentrated cocktail of advanced neurotoxins. Instead of merely degrading tissue like hemotoxins, these complex proteins are engineered to hijack and shut down the central nervous system of the target. Upon injection, these molecules flood the synaptic gaps between the nerve cells and the muscle fibers. They act as molecular blockers, specifically targeting and jamming the acetylcholine receptors. The electrical signals sent by the brain, commanding the muscles to move, are instantly severed. This induces a catastrophic systemic shutdown known as flaccid paralysis. The prey is physically immobilized within seconds, and shortly after, the diaphragm muscles controlling the lungs cease to function, resulting in death by rapid asphyxiation. This extreme neurotoxic potency is driven by a brutal evolutionary mathematics known as biochemical economics. Synthesizing complex venom proteins requires a massive investment of amino acids and metabolic energy. It is an expensive biological weapon to maintain. If a snake strikes, injects its venom, and the prey manages to run a mile before dying, the snake loses its meal and bankrupts its energy reserves. Therefore, natural selection relentlessly favored the individuals, producing the most overwhelming, instantaneous toxins. The venom was continually optimized, not out of biological malice, but to achieve a 100% return on metabolic investment. The prey must drop dead within the immediate strike zone. This exact same selective pressure filtered down into the microscale of the ecosystem, driving the evolution of heavily armed invertebrates. The ancient lineages of funnel-web spiders developed venom structures of terrifying complexity. Their toxins target the ion channels of the nervous system, forcing the nerves to continuously fire without resting, leading to massive physiological overload. In a resource-depleted environment where competition for every single insect and small vertebrate is incredibly fierce, these spiders over-engineered their venom to ensure that whatever they managed to ambush was instantly converted into secured calories. Perhaps the most bizarre and illuminating example of this chemical convergence is found not in reptiles or arachnids, but in the most primitive mammals on the continent, the monotremes. The male platypus possesses a sharp, hollow spur on its hind legs, connected to a highly active venom gland. In the rest of the terrestrial world, the evolutionary strategy of venom in mammals was almost entirely abandoned millions of years ago. Placental mammals solved the problem of competition through advanced brain development, complex social structures, and high-speed cursorial anatomy. But because the Australian plate was completely isolated from this placental invasion, the ancient primitive blueprint of a venomous mammal survived. During the breeding season, when male platypuses engage in brutal territorial combat for the limited resources of the shrinking river systems, they utilize this venom not for hunting, but for intense, localized biological warfare against each other. The venom contains unique defensin-like proteins that cause immediate, agonizing, and long-lasting pain, effectively crippling a rival without killing him. This highlights how deeply the strategy of chemical weaponry is woven into the fabric of the continent. From the massive, hissing reptiles in the dry grass to the small, egg-laying mammals in the rivers, the adoption of venom was the ultimate unifying survival strategy. It was a continent-wide mandate issued by a deteriorating climate. When the environment strips away your calories, you cannot afford to fight fair. You must evolve the capability to terminate a biological system with a single touch. The terrifying, venomous reputation of modern Australia is simply the surviving legacy of a prehistoric world where extreme chemical toxicity was the only reliable way to guarantee that you would live to see the next rainfall. Reconstructing the terrifying biological reality of Pleistocene Sahul requires more than just biological theory. It demands physical evidence. But the Australian landscape is an incredibly destructive environment. The extreme heat, intense ultraviolet radiation, and highly abrasive wind-blown sands actively erase biological material left on the surface. For a giant skeleton to survive for tens of thousands of years, it requires an immediate and highly specific geological intervention. It must be rapidly buried and shielded from the elements in a process known as taphonomy. Fortunately, the unique geology of the continent provided the perfect natural time capsules. The vast limestone karst systems, most notably the Naracoorte caves. Over millions of years, acidic groundwater slowly dissolved the subterranean limestone bedrock of southern Australia, creating massive, sprawling cave networks. In certain areas, the roofs of these caverns collapsed, creating steep, hidden vertical shafts that opened directly to the surface. These holes acted as perfect, inescapable pitfall traps. For hundreds of thousands of years, as giant marsupials blindly crashed through the underbrush or stampeded during massive bushfires, they would fall into these dark abysses. Unable to climb the sheer limestone walls, they perished in the darkness. Flash floods would subsequently wash massive amounts of sand and sediment down the shafts, rapidly burying the remains. Protected from surface scavengers, temperature fluctuations, and ultraviolet degradation, the bones were perfectly fossilized in the silent, dry darkness. However, finding a perfectly preserved fossil is only half the scientific battle. To reconstruct the ecological history of a continent, paleontologists must know exactly when that animal died. For decades, the absolute gold standard of establishing chronological timelines was the radiocarbon dating method. This technique relies on measuring the predictable radioactive decay of the isotope carbon-14 into nitrogen-14 within the organic collagen of the bone. But this biological clock possesses a strict, mathematical expiration date. Because of its specific half-life, once an organic sample reaches roughly 50,000 years of age, the remaining amount of radioactive carbon drops to practically zero. It becomes completely indistinguishable from the ambient background radiation of the Earth. This 50,000-year limit created a massive, decades-long scientific crisis in Australian paleontology. The mass extinction event of the Sahul megafauna, the exact chronological moment when the 3-ton wombats, the giant kangaroos, and the marsupial lions abruptly vanished, occurred precisely along this critical boundary. When scientists attempted to use radiocarbon dating on the bones extracted from the Naracoorte caves or the dry lake beds of the interior, the results were incredibly chaotic, scattered, and utterly unreliable. The dating technology was literally hitting a chronological brick wall. This technological failure created fierce academic debates over whether human beings or climate change killed the megafauna, simply because nobody could accurately plot a timeline to see which event happened first. To break through the radiocarbon barrier, geochronologists had to completely abandon the attempt to date the organic bone itself. Instead, they shifted their focus to the geological matrix burying the fossil. They introduced a revolutionary technique to the continent, known as optically stimulated luminescence dating. This highly advanced method does not measure the decay of radioactive carbon. Instead, it measures the trapped energy of light locked inside individual grains of sand, specifically quartz and feldspar minerals. The atomic physics behind this method are incredibly elegant. When a grain of quartz is blown across the harsh Australian desert and exposed to direct sunlight, the ultraviolet energy from the sun essentially hits a biological reset button. It clears out any stored energy within the crystal structure. But the exact moment that grain of sand is washed into a cave or settles at the bottom of a drying lake bed and is buried underground, it is plunged into total darkness. Deep underground, the sand grain is constantly bombarded by very low levels of natural background radiation emitted by surrounding elements in the soil, such as uranium, thorium, and radioactive potassium. This natural, invisible radiation acts as a slow, continuous battery charge. The radiation physically knocks electrons out of their normal atomic orbits, and these wandering electrons become permanently trapped inside microscopic structural defects within the crystal lattice of the quartz. The longer the grain of sand remains buried in the dark, the more electrons become trapped in these crystal prisons. When a scientist carefully extracts these sediment samples from a fossil dig site, working in total darkness under red safety lights, they bring the sand back to a laboratory. There, they fire a highly concentrated laser beam, the optical stimulation, directly at the individual sand grains. The intense energy from the laser forcefully evicts the trapped electrons from their microscopic defects. As the electrons immediately return to their normal resting state, they release their stored energy as a tiny, measurable flash of light. This is the luminescence. The intensity of that brief, microscopic flash of light provides a highly accurate mathematical measurement of exactly how long that specific sand grain has been buried in the dark. By perfectly dating the age of the sand layer directly below a fossil and the sand layer directly above it, scientists can bracket the fossil, pinpointing its exact age and completely bypassing the 50,000-year blind spot of the radiocarbon method. The application of optically stimulated luminescence was a technological masterstroke that cracked the geological code of prehistoric Australia. It finally allowed scientists to construct a flawless, high-resolution timeline of the Pleistocene epoch, illuminating the exact century when the megafauna collapsed and setting the ultimate stage for analyzing the catastrophic intersection of massive climate shifts and the arrival of an unprecedented new apex predator. For millions of years, the unique flora and fauna of the Australian tectonic plate endured the slow, punishing grind of geographic isolation and a deteriorating climate. They survived by becoming the ultimate biological misers, optimizing every metabolic pathway to conserve energy. But approximately 50,000 to 40,000 years ago, the continent reached a catastrophic ecological tipping point. This was not a single, isolated event, but rather the terrifying intersection of two massive, unstoppable forces. The deep geological cycles of the planet triggered a phase of extreme global aridification, and simultaneously, a completely novel, highly intelligent apex predator breached the oceanic quarantine. The collision of a collapsing climate and the arrival of human beings created a perfect storm of extinction from which the megafauna would never recover. To understand the sheer magnitude of this ecological crisis, we must first examine the global climate mechanisms operating during this era. The Earth was plunging deep into the grip of the Pleistocene glaciations. In the northern hemisphere and over Antarctica, massive continental ice sheets were rapidly expanding, locking up millions of cubic kilometers of the planet's fresh water. As a direct consequence, global sea levels plummeted by over 120 meters, exposing vast tracts of shallow continental shelf. However, the most devastating impact of this global deep freeze was not the cold itself, but the disruption of the hydrological cycle. Because the oceans were significantly colder, the overall rate of global evaporation dropped drastically. The immense weather engines that historically generated the monsoon rains and delivered vital moisture to the Australian interior completely stalled. The localized effect on the Sahul landmass was absolute devastation. The vast, shallow inland freshwater seas, such as the massive Lake Eyre Basin, underwent aggressive and permanent evaporation. They transformed from thriving aquatic ecosystems into blinding, hypersaline salt pans devoid of life. The deep-rooted, nutrient-rich vegetation that blanketed the transitional zones rapidly died off, replaced by incredibly harsh, heavily defended, drought-resistant desert scrub. For the giant herbivores, this was a metabolic disaster. Creatures like the 3-ton Diprotodon or the giant short-faced kangaroos were forced to abandon their historical migration routes. They were pushed to their absolute physiological limits, forced to retreat to the extreme coastal margins of the continent, or to cluster tightly around the few remaining deep-water, subterranean springs and permanent gorges. These isolated water sources acted as ecological refugia, but they also fragmented the megafauna populations into disconnected, highly vulnerable pockets, severely crippling their genetic diversity and their ability to absorb any further ecological shocks. Into this desperately stressed, shrinking, and highly fragmented ecosystem arrived a biological wildcard entirely alien to the Sahul evolutionary tree: Homo sapiens. Crossing the deep oceanic trenches of the Wallace Line region via primitive open watercraft, anatomically modern humans made landfall on the northern shores. This represented an unprecedented event in natural history. For the first time since the tectonic plates separated from Antarctica, a highly advanced placental mammal had breached the quarantine. But humans were not just another predator. They operated on an entirely different set of biological rules. Unlike the marsupial lion or the giant monitor lizard, human beings did not rely on massive bite forces, venom, or sheer biological mass to secure calories. They bypassed the need for extreme internal anatomical weapons by utilizing externalized kinetic energy. Armed with advanced cognitive processing, complex cooperative hunting strategies, and projectile weaponry, they were the ultimate ecological generalists. The invention of the spear thrower utilized the physics of leverage to launch a projectile at lethal velocities. This allowed humans to introduce an entirely novel form of predation to the continent, killing from a safe distance. This technological advantage completely nullified the massive size, thick hides, and lethal close-quarters defensive capabilities of the megafauna. However, more devastating than the spears was the introduction of landscape-scale energy management, fire. Human hunters utilized fire stick farming, a highly calculated practice of intentionally burning massive tracts of the landscape. They deployed high-frequency, low-intensity burns to clear thick, impenetrable brush, promote the immediate growth of fresh green shoots to attract game, and systematically flush out hidden prey. While highly effective for hunting, this artificial manipulation of the fire regime fundamentally altered the botanical and chemical makeup of the continent on a macroscopic scale. The consistent application of fire eradicated the fire-sensitive, slow-growing, protein-rich plant species that had survived in the isolated pockets of the interior. These were rapidly replaced by aggressively fire-promoted, fast-growing vegetation that possessed far lower nutritional values. For the giant browsing herbivores, whose massive, complex fermentation digestive systems were strictly calibrated to extract maximum energy from specific, slow-growing plant types, this was catastrophic. Their primary fuel source was systematically incinerated and replaced by an unpalatable, highly toxic botanical landscape. The intersection of these two forces created an inescapable extinction vortex. Mathematical models of population dynamics demonstrate exactly how species with slow reproductive rates, known as K-selected species, fail under this type of dual pressure. A giant marsupial took years to reach sexual maturity and invested massive amounts of biological energy into raising only a single offspring at a time. Their populations were already naturally low and hovering on the brink of starvation due to the climate-driven collapse of their food and water networks. When human hunters exerted immense pressure from the top down, easily targeting these animals as they congregated in massive numbers around the shrinking waterholes, the mathematics of survival simply broke. If a novel predator increases the mortality rate of juvenile animals by even a fraction of a percent in a K-selected population, the death rate irreversibly exceeds the birth rate. The population can never biologically replace itself. It was the ultimate ecological pincer movement. The deep geological climate cycles squeezed the ecosystem from the bottom up, starving the giants and trapping them in isolated pockets, while humanity arrived to exploit the concentration from the top down. Neither the climate nor the humans alone may have been entirely responsible, but the deadly synergy of a starving landscape and a technologically advanced cooperative superpredator was the final, fatal catalyst that pushed the prehistoric giants of Sahul past the point of no return. For decades, the exact mechanism behind the collapse of the Sahul megafauna has been the subject of a fierce, unrelenting academic war. The central conflict revolves around the blitzkrieg hypothesis, a mathematical model of overhunting originally developed to explain the extinction of mammoths in North America, but aggressively applied to the Australian fossil record. The premise of the model is mathematically flawless. It postulates that a relatively small, highly mobile population of human hunters advancing across a virgin continent could rapidly eradicate massive herbivore populations. Because giant marsupials were K-selected species, meaning they had incredibly long gestation periods, delayed sexual maturity, and produced only one offspring at a time, their population dynamics were mathematically fragile. Computer simulations demonstrated that if human hunters killed just a tiny percentage of the adult population each year, exceeding the natural replacement rate by even a margin of 1 or 2%, the entire species would mathematically spiral into extinction within a few millennia. On a computer screen, the blitzkrieg model perfectly explains the rapid vanishing of the giants. However, a mathematical model is entirely useless if it violently contradicts the physical evidence buried in the dirt. When archaeologists apply the blitzkrieg parameters to the physical landscape of Australia, the hypothesis hits a massive forensic brick wall. In North America, the overkill hypothesis is supported by dozens of undeniable kill sites, where mammoth ribs are found definitively scarred by stone weapons and embedded with Clovis spear points. In Australia, despite decades of intensive excavation across thousands of ancient human occupation sites, there is virtually zero direct archaeological evidence of mass megafauna slaughter. Out of the millions of fossilized bones recovered across the continent, you can count the number of definitive, human-inflicted weapon wounds on one hand. Furthermore, unique archaeological sites like Cuddy Springs in New South Wales present a contradictory timeline. Here, ancient stone tools used for grinding seeds and cutting meat are found completely intermingled with the bones of giant kangaroos and diprotodons in the exact same stratigraphic layers. The geological dating suggests that humans and these massive beasts may have coexisted for up to 10,000 years. This extended timeline absolutely shatters the narrative of a rapid, apocalyptic hunting wave sweeping across the continent. This created a profound scientific deadlock. The mathematical models insisted that humans were the primary executioners, while the archaeological dirt suggested humans were merely bystanders in a climate-driven collapse. To break this deadlock, science had to stop looking for the missing bones and instead search for a completely different biological proxy. They needed a way to measure the actual living biomass of the continent over time, independent of fossilized skeletons. The revolutionary breakthrough came from the microscopic world, specifically through the analysis of a highly specialized coprophilous fungus known as Sporormiella. Understanding the life cycle of Sporormiella is the key to unlocking this prehistoric mystery. This microscopic fungus cannot complete its reproductive cycle in the open environment. Its spores must be ingested by a massive grazing herbivore. The spores physically pass through the animal's complex, high-temperature digestive tract, a process that chemically triggers their germination. The fungus then blooms exclusively in the massive deposits of dung left behind by these giant animals. Because the spores of Sporormiella are incredibly resilient, heavily armored with a thick biological casing, they do not decompose. Instead, they are washed into ancient crater lakes and swamps by the rain, settling into the mud at the bottom. By utilizing heavy drilling equipment to extract deep sediment cores from ancient environments like Lynch's crater in northeastern Australia, paleoclimatologists effectively pulled up a vertical timeline of the continent's biological history. When they placed these sediment layers under high-powered microscopes, they were not looking for climate data. They were counting the exact density of Sporormiella spores per cubic centimeter of mud. The spore count served as a direct, undeniable mathematical proxy for how much megafauna dung was being produced in the surrounding landscape. More spores meant more giant herbivores walking the earth. When the scientists plotted this microscopic data onto a chronological chart, the results were incredibly stark and universally disruptive to the established climate-only narrative. For tens of thousands of years, through multiple severe natural climate fluctuations, the Sporormiella spore count remained consistently high. The giant herbivores were clearly surviving the natural droughts. But then, right around 41,000 years ago, the spore count in the sediment core absolutely plummets. It does not slowly fade, it drops off a cliff, crashing to practically zero in a geological blink of an eye. The megafauna biomass was completely eradicated. The most terrifying and revealing aspect of this data is what happened immediately after the spore crash. Because the exact same sediment core also traps ancient plant pollen and microscopic charcoal, scientists could perfectly align the biological collapse with the botanical record. The data revealed that the Sporormiella crash occurred slightly before the major, continent-wide shift in vegetation and a massive spike in charcoal deposits. This sequence of events completely reversed the traditional ecological cause and effect. The giant herbivores did not starve to death because the continent caught fire and the forests changed. The forest caught fire and changed precisely because the giant herbivores vanished. The loss of millions of multi-ton biological lawnmowers left massive amounts of dry, uneaten vegetation across the landscape, priming the continent for an unprecedented inferno. The fungal spores proved that the sudden biological collapse was the trigger, not the symptom, definitively pointing the finger back toward a sudden, disruptive external pressure that altered the ecosystem faster than climate alone ever could. The abrupt disappearance of millions of giant herbivores from the Australian landscape did not simply leave a quiet, empty savanna. It triggered a violent, cascading failure of the entire botanical infrastructure. To understand the sheer magnitude of this ecological aftermath, we must view the Pleistocene megafauna not just as animals, but as massive, relentless biological engines. A single Diprotodon consumed hundreds of pounds of vegetation every single week. When you multiply that consumption rate by millions of individuals across various species of giant kangaroos, massive wombats, and colossal flightless birds, you have a highly efficient, continent-wide mechanical pruning system. They were the ultimate biological lawnmowers, constantly stripping the canopy, trampling the underbrush, and recycling plant matter back into the soil as highly fertile, rapidly decomposing waste. When this massive herbivore guild was abruptly eradicated, the biological pruning instantly ceased. The immediate, terrifying consequence was the unchecked, explosive accumulation of raw botanical biomass. Because the Australian climate was already shifting toward extreme aridity, dead vegetation did not rot away into soft, damp soil as it does in a wet, tropical rainforest. Fungi and decomposing bacteria require moisture to break down cellulose and lignin. In the dry, baking heat of the Sahul interior, the dead leaves, snapped branches, and towering dry grasses simply desiccated. They stacked up, year after year, decade after decade, turning the forest floors and the open plains into a colossal, continent-wide stockpile of highly combustible fuel. This massive accumulation of dry fuel completely, fundamentally altered the thermal dynamics of the continent. Prior to the extinction event, natural fires caused by dry lightning strikes, or the controlled, localized hunting fires utilized by early human populations, were generally limited in scope. The landscape was a patchy mosaic of heavily grazed areas, preventing a fire from building up unstoppable momentum. But with the megafauna gone, and the fuel loads stretching unbroken across the horizon, the fire regime shifted from manageable, localized burns to apocalyptic, landscape-altering infernos. When a spark hit this unprecedented stockpile, it generated megafires of unimaginable intensity. The thermal output of these blazes was so extreme that it baked the earth, physically altering the chemical composition of the topsoil and instantly incinerating the seeds of the ancient, fire-sensitive rainforest plant species that had managed to hold on through the droughts. This era of catastrophic fire created a massive ecological void, and stepping into the ashes to claim absolute dominance was a botanical opportunist perfectly engineered for a burning world. The eucalyptus. For millions of years, the eucalyptus and its close relatives were just one component of a highly diverse, mixed forest ecosystem. They were relegated to the drier, poorer soils on the fringes of the deep forests. But as the megafires systematically eradicated their broad-leafed, fire-sensitive competitors, the eucalyptus seized the opportunity to aggressively colonize the continent. The eucalyptus did not merely survive the new fire regime, it actively promoted it. It is an extraordinary example of a plant that weaponizes its own environment. The leaves of the eucalyptus tree are heavily saturated with highly volatile, highly flammable essential oils. On exceptionally hot days, these trees literally off-gas a highly combustible vapor into the surrounding air. Furthermore, they evolved specialized bark that does not decay neatly, but instead peels off in long, dry, hanging ribbons. These ribbons act as perfect fire ladders, catching the flames from the burning ground cover and actively funneling them up into the high canopy, creating devastating crown fires that spread at terrifying velocities. The tree essentially attempts to incinerate the surrounding landscape, because it knows that while the intense heat will kill every competing plant species in the vicinity, the eucalyptus itself holds the ultimate biological trump card. Hidden deep beneath its thick, insulating bark, the tree possesses specialized structures known as epicormic buds. While the outside of the trunk may be charred and completely blackened, these dormant buds are perfectly shielded from the lethal temperatures. Within weeks of a catastrophic fire, while the rest of the forest is still a smoldering wasteland, these buds violently erupt, sending out fresh, bright green shoots to instantly capture the sunlight and completely monopolize the newly cleared canopy. In addition, many species possess massive, woody structures underground called lignotubers, which store vast amounts of carbohydrates and nutrients, allowing the plant to completely rebuild itself from the roots, even if the entire upper structure is destroyed. Even their reproductive strategy is heavily tethered to the flames. The tree produces highly durable, woody seed capsules that remain tightly sealed on the branches for years. They are specifically waiting for the intense thermal shock of a fire to melt the resin sealing them shut. Immediately after the fire passes, millions of seeds are dropped directly into the cool, highly fertile, mineral-rich ash bed, completely free from competition and predators. This created a terrifying, unbreakable evolutionary feedback loop that locked the continent into its modern state. Because eucalyptus leaves are so heavily fortified with toxic secondary metabolites, the vast majority of the smaller surviving herbivores simply could not eat them. The dietary niche left completely empty by the extinction of the megafauna remained largely unfilled, save for extreme, highly specialized oddities like the koala, which had to evolve massive, specialized livers and heavily modified digestive tracts just to survive on such a toxic, low-energy diet. Because so few animals could consume the leaves, the vast majority of the eucalyptus canopy eventually dies, falls to the ground, and accumulates uneaten, directly building the fuel load for the next inevitable megafire. The modern Australian landscape, with its sweeping, fire-prone eucalypt forests and its terrifying, cyclical bushfire seasons, is often viewed as a natural, ancient wilderness. But looking through the lens of deep paleontological time, it becomes clear that this is a misconception. The highly flammable, toxic, and harsh environment of today is not the original blueprint of the continent. It is the scarred, heavily mutated aftermath of a prehistoric biological crash. It is an ecosystem permanently locked in a state of highly flammable recovery, a lasting monument to the catastrophic day the giant herbivores disappeared and the broken lawnmower allowed the continent to catch fire. The story of prehistoric Australia is often reduced to a simple catalogue of giant, terrifying monsters. But the true scientific value of uncovering this lost world lies not merely in the immense size of its apex predators, but in the profound ecological warning written directly into its fossilized ashes. It provides the ultimate paleontological case study of exactly how a massive, complex biological network collapses. The megafauna of the Sahul landmass did not fail because they were evolutionary dead ends or primitive biological prototypes. They were, in fact, dangerously over-optimized. By perfectly adapting to a starving, deteriorating continent, the giant marsupials and heavily armored, cold-blooded reptiles completely sacrificed their ecological flexibility. They operated on an incredibly thin metabolic margin, requiring absolute environmental stability to maintain their slow-breeding, high-efficiency life cycles. When you strip an ecosystem of its excess energy, you strip away its biological shock absorbers. The prehistoric Australian food web was a heavily armed, highly specialized glass tower. It could endure the slow, grinding pressure of climate-driven droughts for millions of years. But it completely shattered the exact moment a novel, unpredictable stressor, the technologically equipped human hunter, was introduced into the mathematical equation. This prehistoric biomass collapse forces modern science to look at our current global ecology through a terrifyingly clear lens. Today, ecosystems across the entire planet are facing the exact same deadly synergy that eradicated the giant marsupials. Rapid, severe climatic shifts combined with unprecedented, relentless human pressure. The Pleistocene fossil record proves definitively that nature does not always slowly adapt to dual threats. Sometimes the population dynamics simply break, leading to rapid, irreversible extinction events that fundamentally alter the botanical and thermodynamic reality of a landmass forever. The arid, highly venomous and fiercely combustible Australian outback we observe today is not a pristine, untouched natural wilderness. It is an ecological crime scene. It is the surviving scar tissue of a massive biological crash, serving as a permanent, burning reminder that no matter how terrifying, heavily armed, or massive an organism might be, long-term survival is never guaranteed when the incredibly fragile foundation of the food chain finally gives way.